Okay, so hi everybody, welcome back. Today we're going to be continuing our chapter 13 lecture on fluids, and the next topic to cover in this lecture is Pascal's principle. So let's get into this. So we're going to do a derivation, and the setup is like this. We have a fluid. It's an incompressible fluid, so you can imagine it's water or some other type of liquid which is incompressible. And this is being held in a container, and the fluid is enclosed by a piston. Okay, so this is the piston up here. Now the piston is perfectly free to move up or down without any friction, and the piston itself has negligible mass. Okay? So what we're going to do is come along and push down on the piston with a force that we'll label as Fp. Okay, so it's the force of the push that we apply to the piston. Now, because the fluid is incompressible, even if we push down on it, we're not going to be able to change the volume of the fluid. The volume is going to stay the same. And therefore, that's going to prevent the piston from moving. So the net force acting on the piston is going to equal 0 because the piston is not moving. So let's take a look at the forces acting on the piston before we push down on it and then after we push down on it. So before the push, here's what we have. We have some fluid just below the piston pushing up on it, and then we have air just above the piston pushing down on it. And again, the piston has negligible mass, so we'll ignore the force of gravity. So before the push, it's just the balance of these two forces. The fluid below and the air above are pushing with an equal amount of force. And that means the pressure above and the pressure below are also equal. So the pressure of the fluid below the piston and the pressure of the air above are equal before the push. Now, after the push, we have an additional force going down. Of course, we still have the force of the air pushing down with the same force as before. Now we have Fp also pushing down, and then we have F fluid pushing up, but I'll call this F fluid prime because as it turns out, this is going to be a larger force than before. I need the force of the fluid to counteract these two downward forces, and so I've increased the overall downward force. I'm going to have to increase the force from the fluid to balance that out. So now the pressure in the fluid is greater than the pressure of the air above. So effectively what I've done by pushing down on the piston is I've increased the pressure in the fluid by pushing down on the piston, okay? So that's the idea. The pressure in the fluid must increase to balance out the applied force. Okay, so what we've shown so far is that the pressure just below the piston head in the fluid that's directly in contact with the piston, that pressure is going to increase because of this applied force. So let's say the amount of pressure increase is delta P. So if we call a point just below the piston head, point 1, let's find the pressure increase at some other point, which is a depth d below that, which we'll call point 2. Okay, so let's find the pressure increase over here at point 2. So remember, there's a relationship between pressure and depth in an incompressible fluid, which is P2 would be P1 plus rho times G times D, where D again is the depth below point 1. And so what we can say is delta P2, a change in pressure at point 2, is equal to delta P1, the change in pressure at point 1, and then plus delta, the change in this quantity, rho GD. Well, here's the thing about that last term. Rho is the density of the fluid, G is the acceleration due to gravity, and then D is that distance down that we go. None of these are changing as a result of pushing down on the piston. All of these are just constants which are staying the same throughout this process. So the delta, or the change in this quantity, is 0, which tells us that delta P2, the pressure increase down here, is the same as delta P1, which is the pressure increase up here. So the lesson here is that the same pressure increase is felt in all parts of the fluid. Okay, so if I apply a force to the fluid like this, I increase the pressure everywhere in the fluid by the same amount, same pressure increase. And so that derivation shows us the idea behind Pascal's principle, which is any pressure that's applied to an enclosed, incompressible fluid is transmitted undiminished to every part of the fluid. So remember, incompressible fluids are fluids that don't change their volume when you apply a pressure to them. So liquids are generally incompressible, whereas gases are not. So as an example, if you have a bag filled with water and that bag is perfectly sealed and you squeeze on that bag, you're going to increase the pressure in the water everywhere in that bag by the same amount. So this is one of many discoveries made by Blaise Pascal. So you see this name keeps popping up in our discussion of fluid mechanics because he's made a lot of really important discoveries. And one really important application of Pascal's principle that we use in our everyday lives is in our braking systems in our cars and trucks. So if you like having brakes, you like being able to stop your car, you can thank Blaise Pascal for that. So most braking systems work something like this. You push down on the brake pedal, and when you do that, you apply a pressure to the brake fluid. Now, the brake fluid transmits that pressure through the brake line all the way to the brake calipers. So in other words, the same pressure increase that you apply over here is felt over here at your brake calipers. And that causes the brake calipers to close around your brake disc. So now, as your brake disc is spinning, the calipers are going to be rubbing up against it and creating friction. It's that friction that actually allows your car to come to a stop. Okay, so this is how brakes work. Now, here's an example for you guys to try to work out. We have a cylindrical container filled with water that's enclosed by a piston, as we see here. The diameter of that piston is 19.5 centimeters. The piston is free to move up and down without any friction. So the question is, with what force in newtons would you need to push down on the piston in order to increase the pressure of the water by 2 atmospheres? So let's recall that an atmosphere is equivalent to 1.013 times 10 to the 5 pascals. Now, as a follow-up, if you wanted to achieve the same pressure increase, but by using a smaller force, would you want to use a smaller piston or a larger piston? So pause the video, try to work this out, and then we'll go through it together. Okay, so we'll start by noting that the pressure increase delta P is going to equal the force that you apply divided by the area over which that force is applied. So if we rearrange this and solve for the force, that would just be delta P, the increase in pressure in the fluid, times A. So we want delta P to be 2 atmospheres, right? So we'll just plug that in when it comes time to calculate. But the area is the area of the piston, which is circular. So pi r squared gives us the area of that circular piston. Now r is the radius. We're given the diameter. So remember that the radius is equal to the diameter divided by 2. So the area we're looking for is pi times the diameter divided by 2 squared, or we can write this as 1/4 times pi times the diameter squared, okay? So the force we're looking for is going to be delta P times 1/4 times pi times the diameter of the piston squared, like this. So here we have 1/4, we have pi, and then delta P is 2 atmospheres. But that's the same as 2 times 1.013 times 10 to the 5 pascals. And a pascal is a Newton per square meter. Okay, and then we have the diameter, which is 19.5 centimeters or 0.195 meters, and we square that. So we can see that the units are coming out in newtons. And what you get is 6,050.6 newtons. Keeping 3 sig figs gives us 6,050 newtons, or in scientific notation, 6.05 times 10 to the 3 newtons. Okay, so that's how much force, in this case, you would need to apply. Okay, so now let's take a look at this equation. I'll just write it down again. Delta P, the pressure increase, is equal to the force you apply divided by the area. If we want to use less force, so if we want F to go down, but we want to keep the pressure the same, well, the only way to make that work is for the area to also go down, because the pressure is equal to the force over the area. So if we decrease the force and the area by the same amount, then we can keep the same pressure, okay? So the idea is use a smaller piston if you want to get the same pressure increase with less force. So another application of Pascal's principle is in the hydraulic lever. This is also sometimes called the hydraulic lift. So it's used to lift up very heavy objects. Now there's also something called the hydraulic press, which is used to crush things. And it basically works on the same principle. So everything we're discussing here can also be applied to a hydraulic press. But for now, let's just talk about the hydraulic lever or the hydraulic lift, which is used to lift things up. So basically what this consists of is 2 pistons. We have an input piston over here and an output piston over here. And these 2 pistons enclose a fluid, an incompressible fluid, which is contained down here, okay? Now the thing about the output piston is it has a much larger cross-sectional area than the input piston. So here I'm showing this as a circular cross-sectional area. That would be AO for the output side, and AI for the input side. AO is going to be bigger than AI. So the idea here is if I apply a force at the input end, if I push down on it, well, that's going to increase the pressure in the fluid. And it's going to be the same pressure increase at the input end as it is at the output end, okay? So that means the fluid at the output end is going to be applying an upward force to this piston, and we'll call that force FO. But here's the thing, the forces are not necessarily going to be the same. It's the pressure increase that's the same at the input side and the output side. So because of that, if we have a bigger area at the output side, we're also going to have a bigger force at the output side. So you can have a very small amount of force being applied here, and then you get a very large force at the output end. It's like we're amplifying the force, which is something that a lever does. It amplifies a force, which is why we call this a hydraulic lever. And our starting point is going to be Pascal's principle. The idea here is that the pressure increase in the fluid just below the input piston, because of this force we apply, is the same as the pressure increase in the fluid just below the output piston over here. So let's write down an equation that says delta PI, pressure increase at the input side, is equal to delta PO, pressure increase at the output side. And remember, pressure is force over area, so delta PI can be written as FI over AI, and delta PO can be written as FO over AO. And so if we solve for FO, if we want to know what the output force is going to be, that would be AO divided by AI times FI. And again, the idea here is AO is going to be greater than AI. This is a bigger piston than this one, which means this fraction is going to be a large number. So we're amplifying the force. We're getting a larger output force than the input force. That's the idea. So this amplification of the force, the fact that we get such a large output force compared to our input force, comes at a cost. Because if we look at the distance that each piston moves, so the input piston is going to move down a distance di, and then the output piston is going to move up a distance do. Turns out do is going to be tiny compared to di, okay? And the way we can understand that is by using the concept of incompressibility. That is, even if we're applying really large forces to the fluid is not going to be compressed. The total volume is not going to change as the pistons move. So since the total volume is staying the same, any volume that we move out of the input shaft as this piston moves down is going to have to just flow into the output shaft over here. Okay, so any fluid moving out of this shaft is just going into this shaft. So VI equals VO. That's the idea. Now, the volume can be thought of in the following way. We have a cross-sectional area, A, and then we have a length, D. And if you just multiply those two, we get the volume of this cylinder here, which again is the volume of fluid that's moved out of the input shaft. So that would be AI times DI. And the volume of fluid that's moved into the output shaft would be AO times DO. So if we solve for DO, which is the distance that the output piston is going to move up, that's going to be AI over AO times DI. And again, AO is much bigger than AI, which means the distance that the output piston is moving is actually much smaller now than the distance that the input piston is moving, because this ratio, AI over AO, is going to be a very small number. Okay, so that's the price you pay for getting a larger force, is you don't get to move the piston as far as you're moving this one. So let's do an example. Consider a hydraulic lever with a cylindrical input piston, which has a radius Ri of 15 centimeters, so that's the radius over here, and a cylindrical output piston with a radius Ro is equal to 2.5 meters, so that would be the radius over here. So suppose you want to lift a 1,200 kilogram car using this hydraulic lever. What input force would be needed? We're going to treat both pistons as frictionless and massless. As a follow-up question, how far does the car move up if we push the input piston down 1.5 meters? Okay, so let's work this out. Okay, so we'll start here. Delta PI equals delta PO, that's Pascal's principle, telling us that the pressure increase is the same at each end of the hydraulic lever. At the input end, the pressure increase can be written as Fi over AI, and at the output end, this can be written as Fo over AO. So if we want to solve for Fi, because we want to know the input force in this case, well, that's going to be AI divided by AO times FO. Okay, so we actually know something about the output force. The output force must equal at least the weight of the car if we want to lift it up. So the output force must at least equal the weight of the car to lift it up. So I know that I can set Fo equal to the mass of the car times G. Also, for the pistons, we have A equals pi r squared because they have a circular cross-section. So Fi in that case is going to be AI, which is pi times Ri squared, divided by AO, which is pi times Ro squared, times Fo, which is m times G. So we can cancel out the factors of pi. So we have Ri over Ro squared times mg. Okay, so now let's plug in the numbers. The radius of the input piston is 15 centimeters or 0.150 meters. The radius of the output piston, 2.5 meters. So we're taking that ratio and squaring it. The mass of the car is 1,200 kilograms. And then G is 9.8 meters per second squared. So if you crunch these numbers, you get 42.336, but we'll keep 3 sig figs on that. The units over here cancel in that ratio of RI to RO. And then we're just left with kilograms, meters per second squared, which is a Newton. So 42.3 newtons is the force. Now that's a tiny amount of force. Okay, that's equivalent to about 10 pounds. Okay, so you can take a little 10-pound weight, put it on the input shaft, and that's actually enough to lift the car at the output side. Okay, so that's pretty amazing. But again, the price you pay is that the output shaft is not really moving up that much compared to the input shaft. So to answer the follow-up question, we'll use the fact that the volume that's leaving the input shaft is equal to the volume that's entering the output shaft. And that gives us AI times DI for the input side equals AO times DO for the output side. So if we solve for DO, we get AI over AO times DI, which means we have pi times Ri squared divided by pi times Ro squared times DI. Again, cancel the pi's. We have Ri over Ro squared times DI. So if I calculate that, I'll get the distance that the output shaft moves, or the output piston moves. Yeah. Okay, so let's make the calculation. Again, we have Ri, which is 15 centimeters or 0.15 meters, divided by Ro, which is 2.5 meters, and we square it. And then Di is 1.5 meters. So this works out to 0.00540 meters, which, if we convert this to millimeters, okay, 1 millimeter is 10 to the minus 3 meters, by the way. This is 5.40 millimeters. So the car is only being lifted up a tiny distance. That's the idea. And so I have a follow-up question on that one for you guys to try to work out. In the previous example, calculate the work done by the force on the input piston. So what's the work done by this force Fi? And then calculate the work done by the output piston on the car. In both cases, we're going to give the answer in units of joules. Here's everything we know from our previous calculation. Di is 1.5 meters. DO is 5.4 millimeters. Fi is 42.3 newtons. And then the output force is just the weight of the car, which is mg. So pause the video for a second, try to work this out, and then we'll go through it together. Okay, so remember how we calculate work. W is equal to FD cosine phi. And phi is the angle between the force and displacement. Now, in each case, whether we're talking about the input or the output piston, the angle is just zero. The force and the displacement are in the same direction, right? On the input side, we're pushing down, and it's also moving down. On the output side, we're pushing up, and it's also moving up. So zero in both cases. So we have FD cosine 0, which is just F times D, because cosine 0 is equal to 1. So at the input side, the work would be the F value, the force at the input side, times the distance moved at the input side. So remember, Fi, as we calculated, was 42.336 newtons, and we'll keep 3 sig figs on that. The distance that piston moves is 1.5 meters. So this works out to 63.504 newtons times meters. A newton times a meter is a joule. So this is 63.5 joules when we round it. Okay, at the output side, we have that force, FO times DO. And remember, the force at the output side is just the weight of the car, which is M times G, and then we're multiplying that by DO. So now we have the mass of the car, 1,200 kilograms, times 9.8 meters per second squared, times DO, which is, we calculated this before, 0.00540 meters. Okay, so this works out to 63.504. Keep 3 sig figs. Units are kilograms. We have meters squared on top, seconds squared on the bottom. That's equivalent to a joule. So 63.5 joules. So notice something. The work you put in is equal to the work you get out. Okay, so even though we amplify the force, we're not actually violating conservation of energy or anything like that, because these two works are the same. And so the takeaway point of this follow-up question is that the work you put in equals the work you get out, so the hydraulic lever doesn't violate conservation of energy in any way. So next, let's move on to a new topic, which is buoyancy and Archimedes' principle. Now, to start this off, I'll tell you a little bit about the Greek mathematician Archimedes, who lived a long time ago in ancient Greece, and he made some interesting discoveries about fluids. Now, the first insight is that Archimedes realized that you can measure the volume of an object by submerging it in a fluid. So, as an example, if we have a container filled with water, and then I place an object inside of it, that will displace the water. It will cause the water line to move up in my container. And the volume of my object is just equal to the volume of the water I displace. So in other words, if I see the water line move up by 20 milliliters, it's telling me that the volume of this object was 20 milliliters. He also figured out how buoyancy works. So buoyancy is what we call the upward force that is acting on an object immersed in a fluid. So buoyancy is the force that causes objects to float in a fluid. For example, these ice cubes, the reason they're floating on the surface of the water and they're not just sinking to the bottom is because of this force of buoyancy. All right, so we're going to do a derivation here. And the starting point is this. Let's consider a cube, a solid cube, with dimensions L by L by L. So that's just the length of each side of the cube. We'll call it L. And this cube is submerged in a fluid. And the density of the fluid is what we'll call rho fluid. Okay, that's the density. Okay, so let's draw the cube. And let's indicate the forces that are acting on it. Well, for one, there's going to be a force acting at the top face of the cube, pushing down on it from the fluid above. So let's call this F top. Of course, we'll also have some forces pushing on the sides of the cube. But here's the thing, pressure increases with depth. So as we go farther down, the forces should increase. So as we draw the force vectors going down, I'm going to draw them longer, indicating a pressure increase as we go down in the fluid. But the horizontal forces that I just drew are completely symmetric. So the horizontal forces acting on the sides of the cube will sum to 0. So there's no force to the left or to the right. On the other hand, if we look at the forces acting at the bottom face of the cube, pushing up on it, these will all be larger than the forces I'm showing at the top, because again, the pressure is bigger at the bottom of the cube than at the top of the cube, because the deeper you go into the fluid, the greater the pressure will be. So here's F bottom. So there is an overall net upward force. There is a net upward force because pressure is greater at the bottom of the cube. Okay, so that overall force is what we call the buoyant force. So we'll use B to indicate that. And it would just be the difference between the forces acting on the bottom of the cube and the forces acting at the top. So F bottom minus F top. Let's also remember pressure is force over area by definition. So force is pressure times area, which means we can rewrite the buoyant force as the pressure at the bottom times A minus the pressure at the top times A. Or to write this in a more compact way, pressure at the bottom minus pressure at the top in parentheses times A. Okay, so what can we do with this next? Well, A is the area of a face of the cube. So that would be a square area, which should be L squared. Okay, so we can also remember how pressure changes with depth. The pressure at the bottom of the cube would just equal the pressure at the top, but then I'd have to add to that rho times G times the depth below that we go to get from the top to the bottom. Well, that would just be L, because we're dealing with a cube. We just have to go down the entire side length of the cube to go from the top to the bottom. So therefore, P bottom minus P top is just equal to rho GL. So let's make the substitutions. P bottom minus P top is rho GL, and then A is L squared. So overall what we have is rho times G times L cubed. Okay, so the volume of the cube, let's put this over here. The volume of the cube, that's just L cubed. Okay, so here's what we have. We have rho times G times V now. So next, if we remember the definition of density, which is rho equaling mass over volume, we can put that in here. So we have mass over volume times G times V, which gives us simply mg. And then finally, let's remember that weight, W, is just equal to m times g. So the buoyant force apparently is just equal to the weight. Specifically, we're talking about the weight of the displaced fluid. Okay? When we put this object into the fluid, we displace some of it. And what we found is the buoyant force acting on the object is just equal to the weight of that displaced fluid. And so that's Archimedes' principle. An object immersed in a fluid feels an upward buoyant force that's equal to the weight of the fluid that it displaces. The reason for this, again, is that if you place an object in a fluid, the pressure increases with depth in that fluid. So the pressure on the bottom is always going to be greater than the pressure on the top, which will produce an overall upward force, which is what we call buoyancy. And that makes the object float under some circumstances. So this buoyant force, B, equals the weight of displaced fluid, which is also equal to the mass of the displaced fluid times G. That's what we saw in our derivation, which is also equal to the density of the fluid times the volume displaced times G. So these are just three different but equivalent ways of thinking about how the buoyant force works. We use what we've learned about Archimedes' principle to determine if an object will float or sink if it's placed in a fluid. So the general problem is this. We're going to consider an object that has density rho object. Okay, so this denotes the density of our object here. And it's fully submerged in a fluid, which has a different density, rho fluid. So that would be the density of whatever this fluid is. Now, there are going to be two different forces that are acting on the object. We'll have, of course, the force of gravity pulling it down, or the weight, and the buoyant force pushing it up. Now, these two forces go in opposite directions, so depending on which one is bigger, the object might have an overall downward force that would cause it to sink, or it might have an overall upward force that would cause it to float to the top. Okay, so remember, the buoyant force is equal to the weight of the fluid that we displace by putting the object here. So that would be the mass of the displaced fluid times G. Well, the mass can be thought of as the density times the volume, but we have to be careful about this. Since we're talking about the mass of some amount of fluid, we have to use the density of that fluid times the volume of fluid that gets displaced. Well, the volume of fluid that gets displaced is just the volume of the object, okay? So the buoyant force would be the density of the fluid times the volume of the object times G. On the other hand, the force of gravity, or the weight pulling down on the object, would be the mass of the object times G. Okay, so the force of gravity acting on the object depends on the mass of the object, of course. So that would be, this mass would be the density of the object now times the volume of the object, and then we multiply that by G. So the object will float to the surface if the buoyant force is bigger than the weight. Okay, if the upward force is bigger than the downward force, then it's going to float up to the surface. Okay, so let's say that the buoyant force, which we write as density of the fluid times the volume of the object times G, is greater than the weight, which is the density of the object times the volume of the object times G. And notice how we can just cancel two terms, right? We can cancel out the volume and G on both sides, which means the fluid has a bigger density than the object. Okay, so if the fluid is more dense than the object, then it floats. That's what we figured out. On the other hand, the object is going to sink to the bottom if the weight is greater than the buoyant force. So if W is bigger than B, then it sinks to the bottom. So let's figure out what happens in that case. So we just flip the sign over here to say that the density of the object times the volume of the object times G is greater than density of the fluid times volume of the object times G. And then again, cancel out the volume and G on both sides. This tells us the density of the object is greater than the density of the fluid. So intuitively, we know that if you have a more dense object than the fluid that it's in, it's going to sink to the bottom, okay? So this is stuff that we might intuitively know, but we can actually see it work out mathematically using Archimedes' principle. Okay, so let's do an example problem. So you've probably heard the expression, that's just the tip of the iceberg. So the idea is when you see an iceberg floating in the sea, you only see a very small portion of it. Most of that iceberg is actually underneath the water, so you only see a small fraction of the overall iceberg. So let's actually calculate what that is. Calculate the percentage of the total volume of an iceberg that is exposed above the water. In order to do this, we're going to need to know that the density of seawater is 1,024 kilograms per cubic meter, and the density of ice is 917 kilograms per cubic meter. Okay, so let's work this out. Okay, so we'll start by drawing a diagram. Here's the surface of the water. Here's the iceberg, and most of it is below the surface like this. And there are two forces acting on it, buoyancy pointing up and weight, the force of gravity acting on it pointing down. Now, if we apply F equals ma to the iceberg in the y direction, net force in the y direction is equal to the mass of the iceberg times its acceleration in the y direction. We're going to have the buoyant force with a positive sign, the weight with a negative sign, so B minus W is how we add the forces together. And that should just equal 0 because there's no motion. There's no motion in the vertical direction. So there's no acceleration. Okay, so to take the next step, we'll have to realize that there are two different volumes that are going to come into play in this problem. So we're going to let V total be the total volume of the iceberg. Okay, but then we're going to let V below be the volume of the iceberg that's below the surface of the water. Oops. Okay, so let's indicate V below. It's this volume right here. I'm showing you in the shaded region in the diagram. Okay, now we have these two forces. We have buoyancy and we have the weight of the iceberg. But remember, the buoyant force is equal to the weight of displaced seawater. So what is that going to be equal to? Well, that's the density of the seawater, so I'll call that rho W. And then we have to multiply that by the volume of our iceberg that's below the surface. Okay, so only that much water gets displaced, only V below. And we'll multiply that by G. Again, we're not using the total volume of the iceberg here because the part of the iceberg that's above the surface is not displacing any water. Okay? However, when it comes to W, this is the total weight of the iceberg. So to write this out, we would have the density of the iceberg, so rho I, and then of course it's the total volume that matters here. So if I take the density of the iceberg times the total volume, that's the mass of the iceberg. And then if I multiply that by G, I get the weight. Okay, so we have B minus W equals 0, so we have density of water, V below, times G minus density of ice, V total, times G equals 0. Cancel out G. And what we have is density of water times V below equals density of ice times V total. So V below divided by V total is equal to density of ice divided by the density of the water. So the percentage of our iceberg that's below the surface of the water would be equal to V below divided by V total times 100 to make that a percentage. But again, that ratio of the volumes is the same as the ratio of the densities. So we have density of ice divided by density of water times 100. And so we can actually calculate that. The density of the iceberg is 917 kilograms per cubic meter. The density of the water is 1,024 kilograms per cubic meter. And then we multiply that by 100. This gives us 89.55%. And we'll keep 3 sig figs. So that's the percentage of the iceberg's volume that's below the surface of the water. We want the percentage that's above. So that would just be 100 minus what we found, minus 89.55, which is 10.45, keeping the right number of sig figs. That's about 10.5%, okay? So when you see an iceberg, you're only seeing about 10% of the total. The rest of it is below the surface of the water. Okay, so here's one for you to try out. We have a wooden cube that has a density of 665 kilograms per cubic meter, and it has a length of 25 centimeters on each side. The cube is tethered to a string, which keeps it submerged in salt water, which has a density of 1,029 kilograms per cubic meter. Calculate the tension in the string in units of newtons. So here's the idea. This wooden cube is less dense than the water, so it wants to float up to the surface, but the string is keeping it in place, preventing it from doing that. So we have some tension there. Your job is to find that tension. So pause the video, see if you can get this, and then we'll work it out together. So we'll start by drawing a free body diagram of the cube. And that looks something like this. We have 2 downward forces. We have the weight of the cube, and then the tension in the string is also pulling it down. But the upward force would be the buoyant force. Okay, so these are the 3 forces. If we apply F equals ma to the vertical direction, sum of the forces in the y direction, that equals m times ay. Where we have a positive buoyant force, but tension and weight going down, so we'll put negative signs on those. So the sum of forces is B minus T minus W equals 0, because again, there is no vertical motion for the cube. So if we want to find the tension, well, that would just be B minus W. It would be the difference between the buoyant force and the weight. That gives us the tension in the string. Okay, so we just need to write down expressions for the buoyant force and the weight. So here we go. For the buoyant force, this would be the mass of water that the cube is displacing. So that would be the density of the water, let's call this rho H2O, times the volume of the cube, because it's fully submerged, so that's the volume of water we displace, times G. That's the buoyant force. The weight of the cube would be the density of the wood, so that's what the cube is made out of, times the volume of the cube, times G. So in other words, this right here is the mass of the cube. So of course, if I take the mass of the cube times G, I take the weight. This right here is the mass of H2O displaced. So if I take that mass times G, that's the buoyant force. So what I'm doing is taking the difference between those two. Okay, so now our tension, I can write it in a more compact way, is density of H2O minus density of wood, and then pull out the common factors of V cubed and G. The volume of a cube is L cubed, where L is the length of each side. So then this would be density of H2O minus the density of the wood times L cubed times G. So now we can plug in the numbers. For the density of the seawater, we have, or the salt water, we have 1,029 kilograms per cubic meter. Subtract the density of the wood, 665 kilograms per cubic meter. Then we have L cubed. L is 25 centimeters or 0.25 meters, and then cube that guy. And then G is 9.8 meters per second squared. Okay, so numerically, this comes out to 55.73. We'll keep 3 sig figs. To think about the units, we have kilograms, and in the density here, we have meters cubed on the bottom. But that cancels with meters cubed on top over here. So we're just left with meters per second squared from the last term. So this is a Newton. 55.7 newtons of force is the tension in the string. Okay, so let's do another buoyancy example here. So legend has it that the king of Syracuse asked Archimedes to determine if his crown was made out of pure gold. Gold is known to have a density of 19.3 grams per cubic centimeters. So here we're going to outline an experiment you can do to determine if this crown is actually made out of pure gold or if it's made out of something else. So suppose that when weighed in air, the scale reads 14.7 kilograms. So here we just have a scale. We have the crown hanging from it. The crown is just in air. So the scale now reads 14.7 kilograms. But when we take the same crown and the same scale, and we submerge the crown in water now, the scale is only reading 13.4 kilograms. The reason it's reading a reduced weight is because of the upward buoyant force. So is the crown made out of pure gold or not? That's the question we want to answer. So one other piece of information we need here is that the density of pure water is 1 gram per cubic centimeter. Okay, so let's work this out. Okay, so we'll start by drawing a free body diagram of the crown when it's in the air. So here's the crown, a couple different forces acting on it. We have the tension in the string, we'll call that T, that pulls up on the crown, and it's counteracted by the weight or the force of gravity pulling down on the crown. Now, that's it as far as forces go. Technically, there is a small buoyant force provided by the air. So anything that's immersed in the air is going to feel a buoyant force, but it's usually so small that we can neglect it. So buoyant force from the air is negligible. And so we won't even consider it. Okay, the next thing to note is that the tension force T right here, this is the force that the scale actually reads. Because that string has a certain amount of tension, the other end of the string is connected to the scale. The string is pulling down on the scale with some amount of force. That force is equal to T. So that's what the scale is really telling you, is what the tension in the string is. So if we do F equals ma in the y direction for the crown, in this situation, we have net force in the y direction equals m times ay, Newton's second law. So we have tension going up, weight going down. So we have T minus W equals 0 because the crown is not moving. So here, T is equal to W, meaning the scale actually is reading the correct weight. Okay. So now we'll draw a free body diagram of that same crown when it's in the water. And this time, the buoyant force is not going to be something we can ignore. So here's what it will look like. We'll have the same weight, same force of gravity pulling it down. That's not changing. But now we have a buoyant force pulling it up, pushing it up. And then we also have a tension force pulling it up. It's a different tension force from before, so we'll call it T prime. That's the free body diagram now. So again, we'll apply Newton's second law in the y direction, and we'll get, okay, buoyant force is going up, that's positive. T prime also going up, and then weight going down, and all of that is equal to 0. So we have B plus T prime minus W is equal to 0. But here's the thing. As we just said earlier, the tension is equal to W, or the tension in the first instance, T, is equal to W. So we can make the substitution B plus T prime minus T is equal to 0. Okay, so now let's make substitutions for each one of those terms. For the buoyant force, we have the density of water times the volume of the crown times G. That would be the weight of displaced water due to the crown being there. Okay, T prime, again, that's what the scale reads when the crown is submerged in the water. So we can call this M prime times G. Okay, so this is what the scale reads, is that weight. And T is what the scale reads when the crown is in air, so we can call that M times G. And that equals 0. So here, let me be clear about this. M prime is what the scale reads when the crown is in the water. That's 13.4 kilograms. And M is what the scale reads when the crown is in the air, 14.7 kilograms, like this. Okay, so that's the meaning of these two terms here. Okay, so what can we do with this? Well, first we can cancel out G. That goes away. And then we can solve for the volume of the crown. So I have density of water times the volume of the crown equals M minus M prime. So I'll divide out the density of water to solve for the volume of the crown. So here's how that's going to go. M, that was 14.7 kilograms. M prime, that was 13.4 kilograms. And then we're dividing that by the density of water, which is 1.00 10 to the 3 kilograms per cubic meter. Okay, so this is going to give us the volume of the crown in units of cubic meters. If you calculate it, it's 0.0013 cubic meters. If we convert that to cubic centimeters, we have 100 centimeters in every 1 meter, but we have to cube the entire conversion factor to get this to work, which gives us 1,300 cubic centimeters. So that's the volume of the crown. And this is really important because if we know the volume of the crown, we can then figure out the density of the crown. If we know the density, we can tell whether or not it's gold, because gold has a very specific value for the density. So let's now do the density of the crown. So the density, rho, is equal to the mass divided by volume. So the actual mass is 14.7 kilograms. Remember, when we weigh the crown in air, it's actually telling us the correct weight. So we have 14.7 kilograms, which is 10 to the 3 grams. So 14.7 times 10 to the 3 would be the mass in grams. And then if we divide out the volume, 1,300 centimeters cubed, now we have the density. The units are grams per centimeters cubed. So if you calculate that number, it comes out to 11.3 grams per cubic centimeter. But gold has a density of about 19 grams per cubic centimeter. So this is way off, right? There's no way this is pure gold. It has a completely wrong density. So the answer is this is not pure gold, which means whoever made the crown is probably going to get his head chopped off for this. Okay, so everything we've been doing up until this point is called fluid statics because we're dealing with fluids that are not in motion, they're not flowing, they're not moving anywhere, they're just standing still. That's fluid statics. But we want to be able to also describe fluids that are in motion, fluids that are flowing. For example, the water flowing through a river or water flowing through a pipe, things like that. That would be called fluid dynamics when we now allow the fluids we're describing to be in motion. Okay, so here we're going to begin to talk about fluid dynamics. So to introduce this topic, I want to tell you that there are two basic approaches that you can use to analyze the motion of a flowing fluid. Now, the first one is what we call the material description. You can kind of think of this as like the brute force approach to fluid dynamics. And this involves keeping track of the motion of every single particle in the fluid. So if we're looking at water flowing through a pipe, that would mean I need to keep track of what every single molecule of H2O is doing in that pipe. That would be the material description of the fluid. Now, the other approach is called the spatial description. So here, we're not going to worry about what every single individual particle is doing, okay? That's way too difficult. Instead, what we're going to do is keep track of the density of the fluid and the velocity of the fluid and the pressure at each point in space and at each moment in time. So here's what that would look like. For example, we would have density as a function of x, y, and z. So you'd plug in a position. You'd also plug in the time you're talking about, and it would tell you what the density is. We'd also have pressure, right? The pressure might change depending on your position. It also might change over time. So if you plug in the x, y, and z position and the time, this will tell you what the pressure is. So in the spatial description, we're just trying to find out what these functions are rather than worrying about what every single particle is doing. Now, the material description, where we keep track of what every single particle is doing, is practically impossible to actually do. Because if we just look at like a glass of water, for example, the glass of water has like 10 to the 25th power molecules of H2O in it. So there's just no way we could keep track of the motion of that many particles. So we're always going to stick to the spatial description where, again, we just look at how pressure, density, and velocity of the fluid change with position and how they change with time. So when it comes to the way that a fluid can move, we have two basic types of flow. We call them turbulent and laminar flow. So let's understand the difference between the two. So laminar flow occurs when a fluid moves in organized parallel layers. So let's take a look at this picture here to sort of visualize what laminar flow is. So we have an ashtray. There's smoke rising from the ashtray. And if we look at the smoke down here, we can see that there's laminar flow because the smoke is all uniformly rising upwards in parallel layers. So there's some smoke rising up along this layer, some along this layer, and so on. That's laminar flow. Okay, it's very organized. Everything is moving in the same direction. On the other hand, turbulent flow is chaotic and disorganized. It's characterized by abrupt changes in the velocity of the flow and also the formation of vortices. Okay, so where the fluid seems to sort of spiral in on itself like a vortex. Okay, so we can see the turbulent flow happening over here. Okay, now laminar flow is pretty simple to deal with mathematically. The equations that describe laminar flow are manageable. We can definitely deal with them. Turbulence is extremely difficult. And actually, to this day, we still don't fully understand how turbulence works. There's a lot we know about this, but there are still a lot of open questions as far as turbulence is concerned. So it's not something that's fully understood. And in fact, back in the year 2000, the Clay Mathematics Institute put out what are called the Millennium Problems. So this was a list of 7 unsolved problems in mathematics. Each one has a $1 million cash prize attached to it. So if you can solve one of these problems, you automatically get $1 million. Now, of those 7 problems, only one so far has been solved, and it is not the problem of turbulence. So this is still a problem that no one has solved yet. Specifically, the question they asked is it possible to find solutions to the basic equations of fluid dynamics that precisely tell you when the onset of turbulence is going to occur? So again, if we go back to this picture, we have laminar flow, and then at some point as the smoke rises up, we transition to turbulent flow. So exactly specifying how that transition happens is still something that is not completely understood, but if you crack this problem, you can stand to win $1 million. So needless to say, we're not going to be dealing with turbulent flow in this class. Instead, we're going to stick to laminar flow, which again is much more mathematically straightforward. But I did want to make you aware that we have these 2 types, okay? So the next issue that we might deal with when it comes to a moving fluid is viscosity. So let's consider a fluid that is undergoing a laminar flow. So for example, this could be the water in a river. So here's the very top surface of the water in the river, and here's the very bottom. So this is right next to the riverbed down here. So we have different layers of fluid which are all moving parallel to one another. That's what it means to have a laminar flow. But the thing about these different parallel layers of fluid is that they can exert forces on one another in the direction of the flow, okay? So this type of force between the flowing layers of fluid, it's like friction. You can imagine that each layer exerts a force on the next one, which is analogous to friction. And we call that force viscosity. It's like friction within a fluid. So just like friction, viscosity converts mechanical energy of the moving fluid into thermal energy. Okay, so that would actually end up heating the fluid up, just like friction ends up heating the surfaces up when they slide past each other. So viscosity is going to slow down the flow of the fluid, and it's going to make it heat up at the same time. Okay, that's the effect of viscosity within a fluid. Okay, so this takes us to ideal fluids. Now, as you're probably getting a sense of already, fluid dynamics is complicated. There are a lot of different factors you need to keep track of. So what we want to do, since we're just starting off in this topic, is we want to make things as simple as possible. So we're going to make a number of assumptions, and when we do that, we have what's called an ideal fluid. So an ideal fluid has the following properties. So number 1, we're going to assume that the flow is steady. That is, the properties of the fluid, like pressure, the density, the velocity, things like this, they don't change over time. They stay the same over time. That would be a steady flow. The second assumption we're making is that the fluid is incompressible. Remember, an incompressible fluid is a fluid whose volume doesn't change. So that means the density is the same everywhere within the fluid. And then, of course, the density is also not changing over time. So in other words, the density is just a constant if we assume it's incompressible. The third assumption we're making is that the fluid is non-viscous. So forces within the fluid that resist motion, again, these are analogous to friction, we can ignore them. We're going to ignore viscosity, okay? And then 4, we're going to assume that the flow is laminar, not turbulent. That means the fluid all flows in nice parallel layers, and there isn't this chaotic turbulent motion that we saw earlier. So we're always going to be assuming these 4 things about our fluids when we study fluid dynamics, and that's going to make the equations a lot easier to deal with, okay? So this is what makes an ideal fluid. So as long as we assume that we have an ideal fluid, it has all those properties we just outlined, then the flow of that fluid is governed by 2 equations. So these are the equations that we'll be dealing with primarily when it comes to fluid dynamics. So the first one is called the equation of continuity. This says that if you compare any 2 points within the fluid, 1 and 2, that the area times the velocity stays the same. So A1 V1 equals A2 V2. We're going to go into a lot more detail about what this means and how to apply it later on, but here's the basic idea behind it. When we have a fluid that's in motion, it must move in such a way that its mass is conserved. So in other words, we're not losing any fluid to the outside, we're not taking in any fluid from the outside. The mass of the fluid that's moving stays the same. That's the conceptual idea behind the equation of continuity. Then we also have Bernoulli's equation. Now, this one is a little bit more complicated, but we're doing something similar with it. We're comparing 2 points within the fluid. We're going to compare point 1 to point 2, and there's a certain quantity that stays the same between points 1 and 2. So I'm not even going to go over this equation right now and all the details. I'll just tell you the basic idea behind it. The idea is that the mechanical energy of this fluid is conserved as it flows. Of course, we're assuming no viscosity. So of course, mechanical energy should be conserved if we don't have any viscosity within the fluid. So in the next video, we're going to go into a lot of detail on each one of these equations, do a bunch of examples, but this is essentially a summary of everything we're going to be learning about fluid dynamics. It's right here in these 2 equations. Okay, so that's going to be it for this video. In the next one, we'll go into a lot more depth on these 2 equations and get some practice working with them. So until then, take care. I'll see you in the next one.